Uh, Professor Agarwal, can we start?
Oh, sure.
So good afternoon, dear participants. Welcome to the last session of the International Conference on Special Functions and Applications 2021. Today we have three speakers, Yuri Luchko, Professor Ilmaz Shimshek, and R.K. Parmar. Today's session is chaired by Professor A.K. Agarwal of Punjab University. So before we start the session, let me introduce the chairman. Professor A.K. Agarwal is currently the Professor Emeritus of the Center for Advanced Studies in Mathematics, Punjab University. He has completed his BSc and MSc from Agra University and later received his PhD from IIT Delhi, and has postdoctoral experience at Pennsylvania State University, USA. He has been received several honors. He has published more than 100 papers in international reputed journals. Professor Agarwal is a member of various organizations like American Mathematical Society, Indian Mathematical Society, Ramanujan Mathematical Society, ICSFA, and he has many important contributions in the area of Ramanujan's work. He has introduced the n-color Gaussian polynomials, n-color compositions, and studies their combinatorial properties. And Ramanujan's mock theta functions. He interpreted the Ramanujan's mock theta functions using the colored partitions. So on behalf of the Department of Mathematics, University of Kerala, and on behalf of all the participants, I request Professor A.K. Agarwal to chair the session.
Friends, as you know, that we are now going to start the last session of this conference, and we have three speakers in this session. The first speaker is Professor Yuri Luchko from Germany, from the Technical University of Applied Sciences, and he will be speaking on this topic, special functions in form of convolution series and their applications. It is my pleasure to invite him to deliver his lecture.
Thank you very much, Professor Agarwal. Thank you very much, Dr. Kumar, for your invitation to deliver a talk at this conference. It's really a pleasure for me. And the topic of my today's conference is special functions in form of convolution series and their applications. We start with discussion of the so-called Sonin condition and Sonin kernels, and then introduce general fractional integrals and derivatives with these kernels, and consider convolution series generated by the Sonin kernels. Then we discuss an application of these special functions to derive some explicit solutions to the fractional differential equations with the general fractional integral and derivatives. And then we discuss some references and further results. So let me start with the classical papers written by Abel about 200 years ago. In these two famous papers, Abel constructed a mechanical model, a model for the tautachron, in form of the following integral differential equation. Nowadays, this formula is referred to as the Caputo fractional derivative, but in fact it was introduced by Abel already 200 years ago in the same form. And Abel solved this equation, integral differential equation, according to his model, the function phi at the point 0 is 0, and thus he derived an inversion of this operator in form of the Riemann-Liouville fractional integral. But this object was derived already by Abel. Nowadays, the Abel integral equation is referred to as this integral equation, but historically it was not the case. The Abel integral equation is this one with the Caputo fractional derivative. It's interesting detail, and in the papers, very interesting papers by Abel, he solved this integral equation. The main component of the Abel solution was this formula for the convolution of two power law functions, h alpha and h alpha minus 1. These functions are kernels of the Riemann-Liouville fractional integral and the Riemann-Liouville and the Caputo fractional derivative, and their convolution is equal to 1 everywhere. By h alpha, I denoted this power law function, t to the power alpha minus 1 divided by gamma of alpha. And f star g is just the Laplace convolution. So the main component of the Abel solution was just this formula. And in a paper by Sonin is a Russian mathematician, published 1884, Sonin considered a generalization of the Abel integral equation. He introduced a pair of functions, kappa and k, so-called Sonin kernels, that satisfy this relation. The convolution of kappa and k is identically equal to 1 for all t greater than 0. And then Sonin introduced this fractional integral. Of course, without calling it fractional integral, he just spoke about integral equations. So Sonin considered this integral equation and could derive its solution in form of a derivative of another fractional integral. And it's clear that this solution can be derived very easily. If we construct the convolution of k with the function f, then we have here practically a threefold convolution, and the convolution of k and kappa is equal to 1. So we have just we get just a definite integral of the unknown function phi, and then we can obtain the function phi by applying the first order derivative, and thus we get this solution formula. Nowadays, the operators introduced already by Sonin or in this form are referred to as the general fractional integrals, and these operators are referred to as the general Riemann-Liouville fractional derivatives. But they were introduced already by Sonin, at least formally. Well, some examples of the Sonin kernels are as follows. The most famous example are the power law functions, the function h alpha and h1 minus alpha. They correspond to the Riemann-Liouville fractional integral and the Riemann-Liouville fractional derivative. But of course, there are some other pairs of the Sonin kernels, and the most prominent one introduced already by Sonin consists of a pair of functions in terms of the Bessel function. G is the Bessel function of the second kind, and I is the Bessel function of the first kind. G is the Bessel function of the first kind, and I is the Bessel function of the second kind. There are many other examples of the Sonin kernels. For example, if we take a sum of two power law functions in this form, denoted by kappa, then the corresponding Sonin kernel k is given in terms of the Mittag-Leffler function of this function. So one can consider fractional derivative with this kernel. And recently, some papers were already published regarding the fractional derivatives with the kernel in terms of the Mittag-Leffler function, this one. The Mittag-Leffler function with two arguments is given by this series, of course. Well, in today's talk, we will focus on a special class of the Sonin kernels that was introduced in one of my recent papers. These Sonin kernels satisfy, of course, the Sonin condition, so their convolution is equal to 1. But additionally, the kernels kappa and k belong to the space of functions c minus 1, 0. And this space of functions consists of continuous functions on the real semi-axis, but this function have a singularity at the origin. So the function f1, it's a continuous function, is multiplied with t to the power p, and the exponent p is between -1 and 0. Thus, the function from this space of functions, they have integral singularity of a parallel type at the point 0. Now we introduce general fractional integrals and derivatives with the Sonin kernels from this class, and they are introduced in the same form as it was done by Sonin already. So the fractional integral is just a convolution of the kernel kappa with the function f, and the fractional derivative of the Riemann-Liouville type is the first order derivative applied to the convolution of k with the function f. It's the Riemann-Liouville fractional derivative, and the Caputo type general fractional derivative can be introduced as a regularization of the Riemann-Liouville general fractional derivative in this form. In this talk, we focus today on the general fractional derivatives in the Riemann-Liouville sense. Well, now let's introduce the sequential general fractional integral with the Sonin kernels from this space of function L1. And the n-fold general fractional the integral is just a composition of n general fractional integrals with the kernel kappa. Nothing special, but this composition can be obviously, because of the semi-group property, represented as the fractional integral with the kernel kappa to the power n in the angle brackets. And by this, by f to the power n in the angle brackets, we define the so-called convolutional powers that are defined as follows. If n is equal to 0, then it's just 1. As usual, for n is equal to 1 is the function, it is the function f. And for n greater than 1, f to the power n is the n-fold convolution of the function f with itself. As an example, let us consider the convolution powers of the power law functions. So because of the known Euler formula for the beta function, the convolution of h alpha and h beta can be represented in the form h alpha plus beta. And thus this formula leads to the following formula for the convolutional powers of the function h alpha. H alpha convolutional power n can be represented in the form h n alpha. Well, the sequential general fractional derivative with the Sonin kernels from the space L1 are defined as n times composition of the general fractional derivatives in the Riemann-Liouville sense with the kernel k. It's a very natural definition. And then we formulate now two fundamental theorems of fractional calculus for the sequential general fractional derivatives. The sequential general fractional derivative is a left inverse operator to the sequential fractional integral. It's more or less clear on the space C minus 1, and the space C minus 1 consists of all functions that are continuous on the real positive semi-axis and can possess an integral singularity of the power law type at the point 0. Well, the second fundamental theorem is more interesting, and in fact it was derived only recently in one of my recent papers. If we consider the composition of the n-fold general integral with the sequential Riemann-Liouville fractional derivative, then this composition is the function f of t minus a polynomial in terms of the convolutional powers of the kernel kappa. And the coefficients of this polynomial can be derived in explicit form. Or we can represent this convolution, of course, as the general fractional integral with the kernel k. So the coefficients are given through the values of this composition of the general fractional integral with the kernel k, and the sequential fractional derivative with the same kernel k at the point 0. This formula is very known for the classical Riemann-Liouville fractional integral and Riemann-Liouville fractional derivative. And in this case, we have here just power law functions. For the general kernels, we have here the convolutional powers. Having here this convolution polynomial, of course, it's a natural question to consider the convolutional series. And now we discuss this topic. The convolutional series generated by the Sonin kernels, or more generally by the kernels from the space of functions C-1, are infinite series in this form. These are just series with some coefficients, and instead of the power law functions, we have here convolutional powers with respect to an arbitrary kernel kappa. And this series were called convolution series generated by the kernel kappa. If kappa is identically equal to 1, then the convolutional power coincides with the power law function, and we have just power law series, nothing else. And in the case kappa is the kernel of the Riemann-Liouville fractional integral, this power law function, then we can calculate the convolutional powers of the function kappa in explicit form, and the convolutional series is reduced to this power law series with the fractional exponent of the Mittag-Leffler type. So this convolutional series is a far-reaching generalization of both power law series and power law series with the fractional exponents. Regarding the convergence of this series, there is a very simple and clear result. So if you start with a power law series with this one and assume that the series is a convergent one at a point different from 0, then it's easy to prove that the corresponding convolution series with the same coefficients and with an arbitrary kernel kappa from the space C-1 is also convergent for all t greater than 0 and defines the function from the space C-1. Because we know a lot of convergent series in this form, power law series, then we can construct easily many convolution series that are also convergent. And as an example, let us consider the famous geometric series in this form. And this series, power law series, has a convergent radius not equal to 0, and thus the corresponding convolution series with a kernel kappa from L1 or from the space C-1 is also convergent. And this function that I denoted by L kappa lambda is very important in the theory of the general fractional derivatives, and especially in the theory of the fractional differential equations with these derivatives, because it's nothing else as the function that plays the same role as the exponential function in the theory of the power law series. Let's consider some examples of the convolution series. if kappa is identically equal to 1, then it's easily to calculate, make calculations, and this function L kappa lambda with the kernel kappa is nothing else than the exponential function. And if we set kappa to be power law function, the kernel of the Riemann-Liouville fractional integral, then the convolution series takes the form of the Mittag-Leffler function. And this Mittag-Leffler function is in this form plays a very important role in the theory of fractional differential equations with the Riemann-Liouville fractional derivatives. To proceed with applications, first let's discuss the following very important theorem that was proved recently in one of my publications. This theorem is, of course, completely analogous to the corresponding theorem for the power law series. And it says that if two convolution series with the same generated by the same kernel kappa are identically equal, then it's the case if and only if their corresponding coefficients are equal for all values of the index J. Of course, we are aware of the same result for the power law series, and the proof of this theorem follows the steps of the proofs of the same theorem in the case of the power law series, nothing special. But this theorem is the basis for applications of the convolution series for derivation of analytical solutions to the fractional differential equations with the general Riemann-Liouville fractional derivatives. Let's illustrate this procedure and consider some fractional differential equations. We start with the simplest one, with the so-called fractional relaxation equation in general fractional derivative of the Riemann-Liouville type. And we look for the solutions in the form of the convolution series, in this one. If we substitute this convolution series into the equation, then we have a convolution series with the same kernel at the left-hand side and at the right-hand side of the equations, and they are equal. And that's why we can compare the coefficients of this series and derive some formulas for the coefficients. And by doing this, it's easily derives the solution to this equation in form of the convolution series, in form of this series. B0 is an arbitrary constant because it's a general solution without initial conditions. And you see here that we get the function L kappa lambda. In the case of the relaxation equation with the ordinary first order derivative, we have here, of course, the exponential function. And thus, as you see, we have here the same procedure. And an important question is how to determine this arbitrary constant B0 from the initial conditions. To answer this question, we need an appropriate form of the initial conditions. And this form can be derived from the second fundamental theorem that I already formulated today. So we consider the so-called projector operator, that is a difference between f and the composition of the general fractional integral and derivative. And according to the second fundamental theorem, this projector operator has exactly this form. And the coefficient by the function kappa provides the natural form of the initial condition for the corresponding initial value problem. And thus, to formulate the initial value problem for the fractional relaxation equation, we take the initial condition in this form. So we take the general fractional integral with the kernel k, evaluated at the point 0 and set it to be 0, and then the unique solution of this initial value problem can be given by this formula. In the case of the same equation with the Riemann-Liouville fractional derivative, the kernel k is just this power law function, and the solution to this initial value problem with this initial condition, everybody is aware that for the Riemann-Liouville fractional differential equations, we need the initial condition in this form. We immediately get this known solution formula. And the same procedure can be applied for the inhomogeneous fractional relaxation equation with the source function f. And if we also suppose that the source function can be represented in form of convolution series, then we can derive the unique solution to this fractional relaxation equation in this form. Of course, this the first term is the solution to the homogeneous differential equation, and the second term in form of convolution of the source function f with the fundamental solution L kappa lambda is the particular solution to the inhomogeneous equation. And the constant B0 can be uniquely determined by the initial condition. And the same procedure can be applied in the case of the Riemann-Liouville fractional derivative. Of course, the solution to this equation is very well known and is given by this known formula. That is, of course, a special case of this more general formula. And the same procedure can be applied to other equations, for example, to the multi-term fractional differential equation with the sequential general fractional derivative in the Riemann-Liouville sense, to such equations. And again, we look for the solutions in form of the convolution series and can derive the solution, general solution in this form. So you see here convolution series, and the first n coefficients of this convolution series are arbitrary. So the equation has n linearly independent solutions, and other coefficients can be calculated in terms of this first n coefficients and in terms of the coefficients of the convolution series for the source function f. And of course, the same procedure can be applied to more general equations. And here on this slide, you see how we can derive the natural initial conditions for the multi-term fractional differential equations. We again use the second fundamental theorem and construct the projector operator in form of this convolution polynomial. And the coefficients of this convolution polynomial are nothing else than the natural initial conditions that can be used to fix this arbitrary constant B0, B1, and so on. And the same procedure can be used to apply this convolution power law methods to consider some more complicated, even more complicated fractional differential equations with non-constant coefficients and even nonlinear equations. Well, but let me stop at this point because the time is practically over. And finally, I just wanted to mention some references and further results. The results I presented today are more or less new, and there are also some generalizations of these results and same results about regarding the Caputo form of the general fractional derivatives, operational calculus for these general derivatives with the Sonin kernels, general fractional integrals of derivatives of arbitrary order. You see that all of these papers were published this year So the results are very new, and they already found some applications in physics in the papers written by Vasily Tarasov. He uses general fractional derivatives to suggest the concepts of the general fractional dynamics, of the general non-Markovian quantum dynamics, and even the general fractional vector calculus. The general fractional derivatives was already suggested, but you see that also these results are very, very new. And thus you see that it's a new theory regarding the general fractional derivatives and everything that that is related to these objects. So all of you are invited to contribute to the research regarding this theory and its applications. So thank you very much for your attention.
Thank you very much, Professor Lushko, for your nice talk on convolution series. And you have given nice application also in the fractional differential equations. So I hope that those who are working in this area, they will be benefited immensely. And I don't think that there are any questions from the audience. Are there any questions from the audience? So we thank you again for your talk, for your nice talk. And now I invite the second speaker of this session.
So thank you again for inviting me.
Thank you, Professor Yuri Luchko.
So now we can invite the second speaker. Huh?
Yes, sir. Yes.
Okay. So the second speaker of this session is Professor İlmec Simsek. He's from Turkey, Akdeniz University, Turkey. So please, Professor Simsek. He will be speaking on generating functions for certain infinite sums and their applications. Professor Simsek.
Yeah. Yes, thank you very much, Professor Agaran. And also I would like to thank Professor Dilip. Also thank to all organizer committee who have made big work in this conference. I know really participated conference is difficult, but preparing is very, very difficult. Now I share my screen. How can I share? I do not find I do not find the share.
Professor, there is a share screen button in green.
Yes,
button.
I try. Yes.
Yeah.
Okay. Okay.
And now you can take your slide.
Is okay?
Yeah,
no?
It is visible. Yeah, make
Okay.
it full screen, Professor. Make
Thank
it full screen. Control L. You can press Control plus L.
Control plus L. I think
Not coming.
not coming.
Make it full screen mode is there. In view, it is there. View menu. Not there in the PDF itself. In the view menu, it is there.
I try, but I do not full screen.
Not the second, next one. Not, yeah. Not there, Professor, here. Third one, yeah. Third one. No,
And third.
Yeah, make it full screen there.
Is okay? No?
Yeah, it's okay. Then you can present. Okay.
Okay, thank you very much. Sorry because of delay. Today, I give my recent paper, which is published in Montes Torus Pure and Applied Mathematics. This is, I think there are many interesting applications of certain finite sums involving many known and unknown new final sum and infinite sums related to Dedekind sums, zeta functions, the family of zeta functions, and others. It is very known that generating functions is very big tools, not only in mathematics, but also in probability and in quantum physics and in other engineering areas. Why I give this talk name to this presentation? Because generating functions is very big subject. Final sums is also very big subjects, not only in mathematics, but also in social science and other all sciences. Applications is very difficult in mathematics. Maybe here I give the mathematical applications, not other engineering applications. Maybe due to the time, I skip the abstract. I give some notation. Here we give standard notations of E. N is denotes the natural numbers, Z is integers, and C is denotes the complex numbers. For other notations, in the final sums, 0 over 0, the 0 power 0, here we take 1. The other term goes to 0. This is very important in compute final sums formula. And also these gamma functions, the breaks, lambda breaks over the these indices gives us lambda plus 1 times lambda plus v minus 1. This is very important, not only in hypergeometric functions but also in other rising factorials. This is also here. This binomial coefficients denotes by lambda minus 1 times lambda minus v plus 1 over v factorial. Relation between two symbols is easily, if we replace lambda by minus lambda, we have give relation between these symbols and these symbols. Maybe this is a very important in order to compute Stirring numbers of the first kind. This for first kind is this symbol are used. And second kind Stirring numbers, which here in my talks we give as 2 and k, given by these final sums. And I also use the Bernoulli numbers, which is denoted by Bn. Its generating functions given t over e power t minus 1. This generating function of Bernoulli numbers. And also the maybe everybody knows the geometric functions, hyperbolic, some harmonic numbers and other special numbers. The first, the special numbers is in my talks is Bernoulli numbers. The second is harmonic numbers. This is also given by the genetic functions of logarithm 1 minus z over z minus 1. This is very old numbers. That goes back to earlier times and before him. These numbers, the history of numbers still is very old. And these numbers given by integral representations of the 1 minus x power n over 1 minus x dx. If we give from 0 to 1, if we integrate these functions, this also gives us harmonic numbers. There are many representation of harmonic numbers are given by integral representations. Some of them are mentioned here. Especially if we take in n equals 0, then harmonic numbers goes to 0. The other important family of numbers is generalized harmonic functions. Here, S is any complex numbers, and omega is also complex numbers. If we take these finite sums, here omega is not equal negative integers, and m is any positive integers, then these finite sums gives us generalized harmonic functions. If we take omega equals 0 and s equal 1, we obtain not s equal any k is positive integers, we take the classical harmonic numbers. If m goes to 0, goes to infinite here, it is possible to give Riemann zeta functions here. So the harmonic numbers is closely, generalized harmonic functions closely related to the family of A gamma functions, Riemann zeta functions, and many classical famous zeta and L functions. Yes, here if we take s equal 1, these functions have studied by many analytic number theorists. This is very important in order to give a relation between harmonic numbers and also Euler constant and other identities. Yes. The other tools in my talks is the special functions goes to polylogarithm functions. Polylogarithm functions are given by this series. Here S is complex numbers, and this series convergence for absolute value of z less than 1, and the real S greater than 1. If we take z equal 1 and real S greater than 1, then these functions polylogarithm reduced to Riemann zeta function is given here. Yes, the other cases of polylogarithms, if S equal 1, then these functions reduce to logarithm functions. And if we take z equal 1 over 2, we have logarithm 2. In my recent papers, which is published in Montes-Torres Journal of Applied Mathematics, in this paper, I give new families of numbers, which denote by 8n, x, lambda, and a. Here, x is variable, lambda and a is parameter. The motivation of these numbers are discussed in details in my papers, but some authors and some colleagues wonder why you give 8 here. Why I give 8 here? Because 8 is only indices here. Recently I defined many family of numbers. I mentioned them: A1, A2, Y1, Y2, Y3, Y6, Y7, and Y8. This is only symbol. This does not give any philosophical meanings here. I only give the indices, and in order to classification of numbers, I give only denote by these numbers like this. These numbers is the genetic functions of these numbers. If we multiply by e power xt, this gives us the polynomials. We have the polynomials like this, y8 and x lambda a. These are polynomials. These coefficients this gives by y8 and lambda a. These numbers, these coefficients of these polynomials. It is easy to get the explicit formula of these polynomials if we multiply these functions and these functions by Cauchy product. It is easy. You give explicit formula for these numbers. These are exponential functions. Then if you multiply these two series, it is easy to get the explicit formula. For convergence of the series, I assume that the following restrictions here. And the motivation I mentioned here, the motivation of these numbers is really related to Bernoulli numbers. If we take, for instance, if we take lambda equals 0, then t logarithm a over e power t logarithm a minus 1. These are genetic functions of the Bernoulli numbers. So here only we change t by t logarithm a. So after some easily computations, y8 and 0a is the directly gives us logarithm a power n times bn. Is a bn denotes the Bernoulli numbers. Maybe I make some quick skip the sum of slides because of importance of many new results waiting me. The other motivation of these numbers, if we take a equal 1 and here n equals 0, then we have logarithm lambda plus 1 over lambda. We take logarithm function. If we take lambda equal 1 and for here n is greater than 1, otherwise this goes to 0. Now the other important theorem involving the number y8k is its interpolation functions. By applying many transformations to the genetic functions of these numbers with the analytic continuation or meromorphic continuation and with Hankel contour, it is easy to prove this zeta function. These are zeta type functions, unification of zeta type functions. I here give this name. These very complicated functions, if we look at here, but could you please you focus on this final sums. Maybe the main topics of these talks are focused on these certain final sums here. Why I give some referees ask me, how can you find these final sums? I do not find these final sums come up with in the zeta functions. So I especially target on these final sums. Then I recently prepared many interesting open questions and some interesting problems given on these sums. Maybe I explain some of them. First, if we take a equal a is a base of the logarithm, initial logarithm function, then we take we modify the zeta functions like this. If we carefully look at here, it is related to the gamma functions and also Lash type zeta function. If we take lambda equal 2 and real s greater than 1, this zeta functions is also reduced to the Riemann zeta functions and these functions. This is also zeta type functions, maybe involving harmonic numbers here. Yes. Then interpolation functions of the y8 is given by zeta 1. If we take s replaced by minus k is a positive integer here, then we take the explicit formula for the analytic continuation of the zeta 1 functions by this formula. Special case of this lambda and a reduced to Riemann zeta functions and Bernoulli numbers. Yes, the other special value of zeta 1 is if we take lambda equal a and a equal 2, we have give very nice formula involving Riemann zeta functions and harmonic numbers like this. Yes. Another special case of zeta functions and its interpolation functions, we give the relation between y8 and the harmonic numbers by the infinite series. Yes, it is time to give one special final sums which denote by n lambda. These sums really special of these sums really very decreases very famous, very known final sums. Maybe I mentioned some of them here. The others, if wondering listener send me an email, I send my paper for other applications. Here in the gamma functions, if you replace z by 1 over 1 minus lambda, we take relation between the gamma functions and our final sums like this. And in the sums, if I take lambda equal 2, we get really these harmonic numbers. This gives us relation harmonic numbers identities. These very nice relations here. In my paper, this year I published in my journal, I asked the following question. Really, when I write this paper, I do not aware the solution of this final sums. One of the first questions that comes to my mind like this: what is the genetic functions by n lambda? Did this come from the Z1 zeta functions? Is there other special numbers families related to these numbers? What are the combinatorial application of yn or yn lambda? Can you find any special arithmetic functions representing these families of numbers? There are many questions arises here. Then first, I think that I proved this formula in Revista, I think this is in Journal of Springer in Spain. It's very famous journal. This result are published there. Yn is really depend on harmonic numbers like this. This is known result. This is not my result. This have already known. Then Yn really given like this. And the other relations, inverse sums of inverse binomial coefficients depend on yn minus 1. This is very famous result. This is also known, but I give relation between these and this. And the other maybe in combinatorial applications or in engineering applications is sums of powers of binomial coefficients. This is very difficult question rise in this area. For instance, if you take this differential equation and you solve with t equals 0, you get very nice final sums. This is given by Glomberg, and also Glomberg gives this very nice results also. I read one paper related to watermelon chain problems, which is given by agriculture professors and one application of mathematics. They give some application of sums of binomial coefficients of higher order. When I read this paper, I think that I give another genetic functions for these finite sums involving the sums of sums of powers of binomial coefficients, finite sums. This is really very nice genetic functions which is published in 2019 in Journal of Mathematical Analysis and Applications. Here I give y6. This y6 only I mentioned when I start my talks. This only symbol. These are really genetic functions of the y6. If we make some computation here, this is a genetic function. This the above hypergeometric functions is genetic functions of these numbers. If lambda equals 1 and m equals 0, you directly get the Fractional numbers and other applications. Yes, I removed this section. Then here, these integrals give relation between these integrals and yn numbers I give here. Some formula involving my finite sums. And this is the Catalan numbers relation between these integrals and Catalan numbers and yn numbers are given by this formula. If n equals 0, n equals 1, n equals 2, there are many applications of these integrals. Some of have already known, and here maybe the interesting sections here given by sums of generalized hypergeometric functions. Sums of. Here I give this sum like this: g equals 1 to d, k equals 1 to m, 1 over ag plus k over s. This sums is generalized hypergeometric functions. Harmonic functions. Sorry, not harmonic functions. If we investigate some properties of these sums, then a1, a2, b equals 0 and b equals 1, we directly get generalized harmonic numbers. Here S is complex numbers. And maybe I give reciprocity law of the sums. If we take AG and BG equal 1, G is any finite sums from 1 to B, and B1 minus 1, B2 minus 1, BV minus 1, and we get these sums, and we have this. Then this is very known results. Our sums are related to zeta functions. So this is not my result. These results have already known by in the classical analytic number theory books, you find it. And so we arrive at this very nice result like this, as M as A1, A2, AB is equal, G equal 1 to B, HMS over AG. AG is here the variable of the harmonic functions. Yes, this is very nice reciprocity laws. Symmetric properties. First, I use symmetric properties. If you take a twisted version of the group representation, it is easily you get it. Yes, and then reciprocity law of these sums are given like this. Is a generalized gamma functions. And some I skip because my time is over. I know this sums is also related to hypergeometric functions, and like this here these sums also depend on my finite sums like this. Then so by using these normal results and this derivative formula, we easily get the sums. These sums are depend on this differential equation like this. Yes, the other formula for this, and maybe this hypergeometric functions relations given by Srivastava and Rasas. By using their results, it is easy to give relation between my sums and the other hypergeometric derivative of hypergeometric functions like this. Yes, maybe many Indian mathematicians have studied on Ramanujan results, and also Ramanujan, all results are depend on Dedekind eta functions and like theta functions and others. These theta functions is also related to Dedekind eta functions. I do not mention in detail here. I give if you have A is any Möbius transformation like this, then gamma 1 is a modular group. If we give this transformation formula of the logarithm eta functions, is firstly given by Dedekind in about 200 years ago, 300 years ago, sorry. He's gives like this. It's very nice formula, transformation formula of the Dedekind. Here, as DC is denotes the Dedekind sums like this. The Dedekind sums, these two breaks parentheses given smooth out functions. It is defined by x minus greatest integer functions of x and minus 1 over 2. Then this is a periodic functions. Its period is 1. Then it has a this is odd functions, so its Fourier series are given like this. And then the Dedekind sums has satisfied these relations, and I know I use these sums. Then the reciprocity of the Dedekind sums given like this. Here A and T is the common factor is 1. Then I mentioned SDC plus SCD by SCD. Then SCD is given like this, and BCD is given by this. These numbers are all A and C and D's common factor is equal 1, and these positive integers. Then this, how can we compute these finite sums? If C and D is co-prime. For instance, if we take M equal 10 and D equal 2, then we give this sums expanded like this. Yes. Now, how can we sum reciprocity law of the Dedekind sums by using these certain finite sums? After some elementary computations, here is denotes the harmonic numbers. We give this formula. Yes, the another formula. here I change the functions, HC and F. Then my final sums, if it take lambda equal 1/2, is really depend on very nice final sums which come from Dedekind sums and Dedekind function like this. This, yes, I mentioned this theorem, and the other important final sums given explicit formula of these sums is very complicated sums are given by this special numbers like this very special formula. This here is harmonic numbers HM. Yes, the other reciprocity law for the final sums. This is very nice formula is also in this paper given like this. And sorry, I am skip very quickly. The special value of the above sums, if C and T is equal 1, the common factor is equal 1, we get a very nice formula like this. This is a very nice formula for this final sums. Yes, now I compute some of the above values for yn lambda is given by this table. And it is time to give another question, open question for young researchers in order to they improve their thesis or their papers. Here I give S5 is Hardy sums. Hardy sums come from the transformation formula of theta functions. Yn k is defined by me about 15 or 20 years ago, which is published in Taiwan Journal of Mathematics. This is Yn sums is defined by depend on Dedekind Hardy sums, which is then depend on Dedekind sums, and by using these functions, it's with its Fourier series, then by H satisfy this reciprocity law. By using this reciprocity law, how can we compute the above formulas? This is really, I do not compute them. What kind of the result of obtained when the method is given like the Dedekind functions? How can we prove by using these sums? How can we prove and find the new final sums? And also, this is also another very nice final sums depend on generalized Hardy sums. And how can we compute these sums if K and H is common factor is equal 1? It's very, very big question. And maybe solving them is give you big energy and big knowledge stay behind this question. Maybe you use this formula. I give some clue and some way in order to prove this. Maybe I closed my section about 5 minutes. I take more. Sorry, Professor Agarwal. After 1 minute, I complete my talk. Some references. This is a very nice paper for the Dedekind sums and there's transformation formula given by Upstall. And in other very nice paper is also given by Bayat, which is published in Montestor's Journal of Pre-and Mathematics. Really is very high quality, it's about 775 page. I'm not good. And the other, these papers also depend on Srivastava and Choi, who are famous in this area, especially in the area of zeta functions and harmonic numbers. And also, I give maybe some people focus on the following numbers, especially my recent paper is this and this and also this. It's a very nice result for the final sums of the certain final sums involving Poisson numbers. Thank you very much for your.
Thank you. Thank you very much, Professor Semse. You have given a very interesting talk, and the problems which you have posed, they are really interesting. It would be of great interest if somebody can find relationship with some known combinatorial objects. As the Bernoulli polynomials and Catalan numbers, they have many interesting combinatorial properties. So it is possible that somebody can find combinatorial properties of these numbers also by MK. You have given a very interesting talk. Thank you very much for this.
Thank you very much.
And
thank you very much.
Are there any questions from the audience? So if there are no questions, then I'm inviting the last speaker of this session, Dr. R.K. Parmar. Last speaker of this session, Dr. R.K. Parmar from Department of Mathematics, University College of Engineering and Technology, Bikaner. He will be speaking on the topic multi-parameter Matthew and alternating Matthew series. Dr. Parmar?
Yes,
is he
sir.
Here?
Yes, sir. Good afternoon,
please.
sir.
Good afternoon. Please start your lecture.
Yes, sir. So is the slides are visible, sir?
Yes, they are visible.
Good afternoon to all of you. Thank you, Professor A.K. Agarwal, sir. My talk is on multi-parameter Matthew and alternating Matthew series. This work is joint work with Professor Gradimir and Professor Tibor K. Pogan. Since special functions are some particular mathematical functions which have more or less established names and notations due to their importance in mathematical analysis, functional analysis, physics, or other applications. However, there is no general formal definition, but the list of mathematical functions contains functions which are commonly accepted as a special function. In particular, elementary functions, especially trigonometric functions, are also considered as special functions. Especially these functions commonly arise in such areas of application as heat, conductions, communication system, electro-optics, nonlinear wave propagations, electromagnetic theory, and electric circuit theory, and many others. The theory of special functions have been developed essentially in the 19th century due to contribution of C.F. Gauss, Jacobi, Klein, and many others. Because of their remarkable properties, special functions have been used for centuries. For example, since they have numerous applications in astronomy, trigonometric functions, so I have studied for thousands of years. However, in the 20th century, the theory of special function has been overshadowed by other fields such as real and functional analysis, topology, algebra, and differential. All the same in that time appeared in G.N. Watson books entitled "A Treatise on the Theory of Bessel Functions," which is a very important book in the theory of special functions, especially in the asymptotic expansion of Bessel function. In this talk, we will study about the main objective of this work is to present a multi-parameter study of familiar Matthew series and alternating Matthew series. These alternating Matthew series and familiar Matthew series expansions are obtained in terms of Lorentz-Illah's hypergeometric functions by using generalized Weber-Sefetelin integral. Relationships of the multi-parameter Matthew series and alternating Matthew series with the Riemann zeta and the Dirichlet eta functions are also considered here. Another set of bounding inequalities are presented for the hyperbessel and Bessel-Clifford functions, and also some log convexity and Turan type inequalities are considered for the extended Matthew type series discussed here. Before starting, I give the definitions of some preliminary definitions. The series representation of Riemann zeta function, zeta s, is defined by zeta s is equal to summation n greater than is equal to 1 1 upon n raised to power s. And its integral representation is given by zeta s is equal to 1 upon gamma s 0 to infinity x raised to power s minus 1 upon e raised to power x minus 1 dx, and is defined in 1.1. The close relative of the Riemann zeta function known as Dirichlet eta function or alternating Riemann zeta functions eta s, and its integral representation is given by eta s is equal to summation n greater than is equal to 1 minus 1 raised to power n minus 1 upon ns n power s, and integral representation is neta s is equal to 1 upon gamma s 0 to infinity x raised to power s minus 1 e raised to power x plus 1 dx, and it is defined in 1.2. In the study of elasticities of solid bodies, E.L. Matthew investigated the functional series of the form SR is equal to summation n greater than is equal to 1 2n upon n square plus r square whole raised to power 2. And it is presented in equation number 1.3. A remarkable useful integral representation for this Matthew series given by Emerson in the following elegant form. SR is equal to 1 upon r 0 to infinity x sine rx e raised to power x minus 1 dx. The alternating Matthew series S bar r given by n greater than is equal to 1 to infinity minus 1 raised to power n minus 1 2n upon n square plus r square whole raised to power 2 where r greater than 0, and it is, and one of its integral representation is given by S bar is r is equal to 1 by r 0 to infinity x sine rx upon e raised to power x plus 1 dx. This series and integral representation is defined by Pogani. Various other kinds of Matthew series are also studied in various papers. The Matthew series 1.3 and alternating Matthew series 1.5 can also be written in terms of Riemann zeta function and Dirichlet eta functions given by the relation SR is equal to 2, n greater than is equal to 0 minus 1 raised to power n, n plus 1, zeta 2n plus 3 r raised to power 2n, and S bar r is equal to 2, n greater than is equal to 0 minus 1 raised to power n, n plus 1, zeta 2n plus 3 r raised to power 2n. It is presented in 1.7 and 1.8. It can easily derived by the series representation of by the integral representation of 1.4 and 1.6 by the expansion of binomial expansion of e raised to power ex plus 1. In the big, also some definition of hypergeometric Bessel type is elementary definitions. In the Fox-Wright function, which is generalization of hypergeometric function, is defined as p psi q, and it is defined in the series representation of ratios of product of gamma functions, and it is given in 2.1 with the convergence conditions presented in 2.2. The Fox-Wright function extends the generalized hypergeometric function PFQ with which power series reads by PFQ and is given in the form of summation k greater than is equal to 0 to infinity product of Pochamber symbols or ratio and divided by product of Pochamber symbols, where Pochamber symbol is defined by gamma k tau plus k upon gamma tau. In the special cases, AR is equal to BS is equal to 1 and R is equal to 1 to P, where S is equal to 1 to Q, the Fox-Wright functions P psi Q reduces to the generalized hypergeometric function, and it is presented in by the relation this. Also, the Bessel function of the first kind of order nu has the power series definition, which is presented in 2.3. While the modified function of the modified Bessel function of the first kind of order nu has the series expansion of I nu is equal to z, k greater than is equal to 0, z by 2 raised to power nu plus 2k upon factorial k gamma nu plus k plus 1. their multi-parameter analogs are the hyperbasal functions by Deleuze has the power series definition, which is given by J nu m z by m plus 1 whole raised to power summation j1 to m nu j series k greater than is equal to 1 minus k greater than is equal to 0 minus 1 raised to power k z upon m plus 1 power k m plus 1 gamma nu 1 plus k plus 1 product of s there and gamma nu m plus k plus 1 factorial k. Its modified version is given by this. Now, if we put m is equal to 1 in this, we get classical Bessel functions, definition of classical Bessel and modified Bessel function. While for m greater than is equal to 2, we deduce the so-called Bessel-Clifford or normalized hyperbasal function given by 2.4. In the case m is equal to 1, the Bessel-Clifford function is related to the standard Bessel function of the first kind of order, nu1 is equal to nu given by the relation 2.5. Another type generalization includes the multivariable Lauricilla generalized hypergeometric series of m variable. We apply FCM. Its definition is given by FCM alpha beta gamma x summation k greater than is equal to 0 alpha Pocamber symbol alpha k1 plus k root km beta k1 plus k2 to km and product of 1 to m xj raised to power kj gamma j kj factorial. The convergence condition is given by root x modulus x1 root plus dash dash root modulus xn root less than 1. Also, the Srivastava-Dost generalization of Lauricilla's hypergeometric function in m variables defined by 2.6 and it is denoted by S. Here, bracket A denotes the sequence of A parameters and empty products should be interpreted as infinities. And Srivastava and Dost reported that the series 2.6 converges absolutely under the conditions given by 1 and 2. Now we start by the multi-parameter Matthew series. We extend the Matthew series SR and alternating Matthew series SR by 3.1 and 3.2. This is defined by S mu nu R root pi by 2R 0 to infinity x raised to power mu minus 1 e raised to power x minus 1 j nu rx dx. Another alternating Matthew series is S bar mu nu R root pi upon 2R 0 to infinity x raised to power mu minus 1 e raised to power x plus 1 j nu rx dx. Now, if we put nu is equal to half, this Matthew series 3.1 and 3.2 reduces to the classical Matthew series. Here, now we introduce the multi-parameter analog of Matthew series and alternating Matthew series, which is defined by 3.3 and 3.4. Here, in this definition, we have taken the product of Bessel function. Now, if we put the relation 1 upon e raised to power x plus 1 is equal to 1 upon e raised to power x minus 1 minus 2 upon e raised to power 2x minus 1 in the equation 3.3, in the equation 3.4, we get the relation, simple interrelation this. Now, this multi-parameter Matthew series and alternating Matthew series can be written in the form of Lauricilla's hypergeometric function. This is given by in this form and in this form. This can be derived by using the series expansion of binary series expansion of kernel e raised to power x minus 1 raised to power minus 1 by writing summation n greater than is equal to 1 e raised to power minus nx into the equation 3.3 and changing the integral sum in, we obtain equation 3.5. Now using the integral representation of generalized Weber Cephetalin, which is represented by 3.6 in this integral representation. If we use this integral Weber Cephetalin integral in 3.5 and taking alpha is equal to n and beta j is equal to rj, we get the first result in the form of Laurentilla hypergeometric function. For second result, if we take the binomial expansion 1 plus e raised to power x whole raised to power minus 1 as summation n greater than is equal to 1 minus 1 raised to power n minus 1 e t raised to power minus nx in this integral in second for the second series for the second alternating series, and using again this integral we get the second result for the alternating multi-parameter Matthew series. Another results is defined by if we take m is equal to 1, if we take m is equal to 1 in this 3.3 and 3.4, we get the equation 3.1 and 3.2. It means one parameter Matthew series. Now, in this result, if we take m is equal to 1, the Laurentilla hypergeometric reduces to the classical, the generalized hypergeometric function, and these results can be rewritten as for the one parameter Matthew series, this and this. It can also be derived by another method by using the integral representation of 0 to infinity x raised to power mu minus 1 e raised to power minus ax j nu bx is equal to b by 2 nu gamma mu plus nu upon a raised to power mu plus nu gamma nu plus 1 2f1 half mu plus nu plus 1 nu plus 1 minus b square upon a square. Also, if we use this integral representation in the 3.1, we can also derive same formula, same relation from that integral also. Now, the reconstruction of the sine functions product in multi-parameter series integrand in 3.3 and 3.4 gives the another associated integral represented in terms of sine function. If we take nu1 is equal to nu2 is equal to nu3 is equal to dash dash is equal to for nu m half, all the new parameter, if we take half in this relation, equation 3.3 and 3.4, we get this integral this integral representation as product of sine functions, here reported as 3.7 and 3.8. Now, if we put m is equal to 1 in 3.7 and 3.8, we get again classical integral representation of Matthew series and alternating Matthew series. If we take m is equal to 1 and mu is equal to 5 by 2 in this equation 3.7 and 3.8, we get, I already defined, we get classical definition of Matthew series and alternating Matthew series. Again, the series representation for these Matthew series 3.7 and 3.8 can be written as in terms of Laurentilla hypergeometric function fc, and it is presented by corollary 1.2. Now, these multi-parameter Matthew series can also be written in terms of Riemann zeta function and Riemann eta function, Dirichlet eta function, and it is presented in theorem 1 under the given condition, and the relation for the Riemann zeta function is this, and for the alternating Matthew series, and it is given in the relation of Dirichlet eta function. If we use the Bessel function series in 2.3 and in the Bessel function series form 2.3 in 3.3 integral of multi-parameter Matthew series, and changing the integration and summations and some elementary step, and then finally using the definition of Riemann definition of integral form of Riemann zeta function in this, for this integral, we get the first relation of this series in terms of Riemann zeta function. Also, for second integral, if we again use the definition of series representation of Bessel function, and again using the integral here, this integral here, it will be given the result in form of ex plus 1, and using the definition of Dirichlet eta function, we get again second result in terms of Dirichlet eta function. Now, for nu 1 is equal to nu 2 is equal to nu 3 is equal to nu m is equal to half. If we take the value half, we get this theorem. We get the corollary by this theorem for the sign product, for the product of sign. And it also can be represented in terms of zeta and eta function, and it is given by 3.9 and 3.10. This Matthew series, this multi-parameter Matthew series 3.1 and 3.2, 3.3 and 3.4 can also be generated in another way by using the product of Bessel-Clifford functions in the integral, and we get the hyperbessel function generalized Matthew type integral representation and its alternating versions given by 4.1 and 4.2. Now, for this series representation, for this integral representation, we have to evaluate the series representation, which we will give in the terms of Srivastava-Dost function S. For this, we have to find one integral representation or Laplace transform for this function. For this, if we want to find the Laplace transform of product of this Bessel function, Bessel-Clifford function, and this functions, and this can be evaluated and can be written in terms of Srivastava-Dost function by 4.3, and similarly for modified Bessel function, it can be represented in terms as 4.4. The proof is very simple. If we express the hyperbessel function by their Maclaurin series representation and some routine calculation, we can obtain 4.5, and again using the definition of Pochamber symbol notations in 4.5 and using the definition Srivastava-Dost S functions, we can easily obtain 4.3. And similarly, the proof is similar for the 4.4. Now, the multi-parameter extension in terms of Bessel-Clifford function can be written as in terms of series representation in terms of Srivastava-Dost function as given by theorem 3, and it is this relation and this relation. This is for alternating version, and this is for the multi-parameter Matthew series, and this is for the multi-parameter alternating version. Derivation follows the similar method as for the theorem 1, and using the series expansion of this, and by using the Laplace transform, we can easily obtain the derivation of this result in first result for the theorem 3. And similarly, if we use the series expansion for the plus for the alternating, we can easily obtain this result also. these are the corollaries which we can take if we take the Lj. In this, if we take this L parameter, Lj is equal to L, whole L. If we take one more special case, Lj is equal to L, all Ljs are equal to L, we can again obtain another result for this version is theorem for corollary as given by corollary 3.1. Now, if we take another, it is also another Bessel M product of M Bessel Clifford function, and we replace by the hyper Bessel function in the definition 4.2, 4.1 and 4.2. The another extension will be defined by 5.3 and 5.4. And again, by using same procedure, Srivastava-Dost relation and the Laplace-Mellin transform of this function, these series can also be represented in terms of Srivastava-Dost function. Here we represent in theorem 4. The proof is similar as in given by earlier theorem. And same Srivastava-Dost function. If we take m is equal to 1 in Srivastava-Dost function, the function reduces to the generalized hypergeometric function, and these results can also be written in terms of generalized hypergeometric function if we take m is equal to 1. Here, these results are represented by 5.5 and 5.6. Also, these results can be written in terms of Riemann zeta function and Riemann Dirichlet eta function, here given by corollary 4.2. Some functional bounding inequalities we have also find out. For estimation purpose, we recall certain bounding inequalities for Bessel functions. Here, we mention the von Lomel's results given by 6.1, Meenakshi Sundaram and Sajad results 6.2, and Landau's bounds for Bessel functions 6.3 and 6.4. Here, if we take these functional bounds in results 2.1 and 2.2, we can obtain some bounds for the Matthew series, extended Matthew series, and alternating Matthew series, and here it is represented by theorem 3.5. These results can derive very easily if we take the transformation of Bessel function in the integrand as follows: J nu Rx is equal to J nu dot R upon nu x, and now applying the Paris bounds in this result, we get 6.13. Now, putting 6.13 in and splitting the integral of extended multi-parameter Matthew series, we get two parts of this integral. And if we solve first part, and in second part, if we use Landau's first upper bound, and for first part of this sum, if we evaluate, and it can be written in terms of Riemann zeta function, and for second function, it can
Dr.
also
Parmar,
be. Yes,
sorry
sir.
for interruption. Could you please skip the proofs?
Yes, sir. Moreover, we have also found the bounds for the multi-parameter here presented by 6.16. Also, some log convexity properties we have discussed here for these defined multi-parameter Matthew series. The relations for these log convexity is given by in theorem 10, and also here these relations can be written in for that we can get Turan type inequalities as 7.1. This research work is supported by Matrix DST. All thanks to convener and all ISFA organizing committee. These are the references which we have discussed. Thank you, sir.
Thank you, Dr. Parmar, for your nice talk.
Yes,
you have done a lot of work in this area,
yes,
and the work which you have presented, it is a joint work with two other mathematicians, I think.
Yes, yes, sir.
Have you published it or not yet?
Yes, sir. This is published in Applied Mathematics and Competition.
Okay, which year?
Just in March month. Yeah, 2-3 months.
Okay, you are doing a lot of work in this area. Thank you. Thank you very much for your talk.
Thank you.
So now I thank all, this was the last talk. So I conclude this session and I thank all the three speakers of this session. And I take this opportunity to congratulate Dr. Dilip Kumar for organizing this conference very successfully. Thank you all. Okay.
Thank you.
Thank you, sir. Thank you for your nice words, and thank you very much for chairing the last session of ICSFA. In fact, before the sessions, I would have to introduce the speakers. So I just, in a quick line, I just share some few words about the Professor Yuri Lushko. He's a professor in Faculty of Mathematics, Physics, Chemistry in Technical University of Applied Science, Berlin. He has completed his master's from Belarus State University, Minsk, and received his PhD from the same university. And he has been awarded a postdoc from Free University, Berlin. And later he became the full professor of the Technical University of Applied Sciences in Berlin. So his main areas are fractional calculus. He has co-authored many books and he has more than 100 publications to his credit and more than 9,000 citations to his credit. So I thank you, Professor Yuri, for presenting his work. And Professor Yilmaz Şimşek was the second speaker. He is he's from Akdeniz University, Turkey, and he's received from he received his PhD from Kurkova University, Adana of Turkey, and his main areas are modular forms, p-adic analysis, Q-series, special functions, special polynomials, and generating functions, and many other areas also. He has published more than 200 papers and has written many books, and he is a referee of many international and national journals. Thank you very much, sir, for participating and presenting your work. Professor R.K. Parmar is an assistant professor at University College of Engineering, Bikaner. And in fact, he is the organizer of the last offline conference of SSFA. So his main areas are special functions and work many areas in fractional calculus and also in Q-series. So on behalf of the Department of Mathematics, I extend our sincere thanks to Professor Parmar also. So thank you very much
Thank you,
to all the speakers. And we are just moving to our valedictory function. So I hope everybody is present. I think Bhargava sir. So yes. Shall we have an video on so that we can have a one snap together?
Yeah, I have my video on.
So that since most of the people are present now, I request all of you to switch on your video so that we can have a snap, and later we can move it to the formal valedictory function.
Yeah, I have mine on. Professor Dilip, I am
yes.
on. I am on.
Yeah, I can see, sir. I can see. I request participants to switch on your camera if possible. Yeah.
Dilip Kumar, you
yes,
look like,
yes, sir. I am just copying that screenshots.
you look like
I was just copying the screenshots.
You look like.
Thank you very much. Thank you very much, participants, for switching on your videos. So we are moving to the valedictory function. So for this valedictory in a one line, I welcome all the executive committee members of SSFA, as well as all the participants and all the chairs, all the speakers, all the crew members who were working hard for making this conference successfully. I welcome all of you to this valedictory function. And I now request Professor Bhargava to say a few words.
Thank you, Professor Dilip. Friends, there is a saying to the effect, even good things have to come to an end, but only for a new beginning. So here we are to bid farewell to each other and to, at the same time, look forward to meeting again in future, near future, I should say. I'm sure that the participants have greatly benefited from this meeting for the society, 20th annual meeting, bringing themselves abreast with latest research in their respective areas of interest, availing the opportunity lent by various speakers from our country and abroad, who spare their valuable time and share their own frontier knowledge. Special mention has to be made of the annual feature, namely the lecture in memory of the founding father of this society, Professor R.P. Agrawal, the lecture being delivered by Professor Ken Wono. The success of this wonderful 3-day academic meet has been possible because of the meticulous, diligent, and impeccable planning and execution by the entire University of Kerala team and executive committee members of the Society for Special Functions and Applications. Honorable Minister of Higher Education, Dr. Bindu, who made herself free to grace the occasion, brought to the knowledge of the audience about her government's vision of founding institutions for interdisciplinary studies. This is consistent with the ubiquitous role played by the theory of special functions, not only within mathematics, but science at large, and engineering, and possibly in other disciplines as well. In conclusion, I'd like to thank her and congratulate the University of Kerala team, headed by its Vice Chancellor and Pro-Vice Chancellor, and the members of the BC of SSFA for making this meet possible and a grand success in spite of the existing pandemic. Thank you all. I can move on to the next.
Thank you, Professor Bhargava, for your nice words of motivation. And next, I request Professor Ahmed Ali to say a few words, as our Secretary of SSFA is not present here. So I would request Professor Ahmed Ali to say a few words.
Thank you, Dr. Dilip. So we have come to an end of this 3 days conference, which was one of the successful conference, as we have heard a number of eminent mathematicians, and their talks were very motivating, and especially for the young students who are tuning in. In fact, during the last 3 days, we had 11 sessions, 21 talks, around 80 paper presentations. And I really appreciate the efforts made by you and your team for making this conference successful. I would also like to put on record the supports of each and every member of the Executive Council of Society for Spatial Functions and their applications, especially the President, Professor Bhargava, and Vice President, Professor Kalyan, and all other members. Dr. Dilip, accept our congratulations for this successful organizations and convey our gratitude to all your team members. I would also like to thank all speakers, all chairs who were so cooperative, and all the participants for their active participations. We are organizing this conference in offline mode due to the current pandemic situations, and let's hope that next conference, which will be the 21st meeting of the Society for Spatial Functions and their applications after a year in 2022. We hope that we'll be able to organize, situation will improve, and we'll be able to organize it in an offline mode, and we'll be able to meet each other and interact physically. So thank you, Dr. Dilip, once again, and congratulations, and thanks to everyone. Thank you. And
thank you.
There is one more thing. So many people are present here. I was getting a query about the proceedings of the conference. Just would like to mention that soon we will come up with the final information and announce the date of the submission of the manuscripts for proceedings. We'll make a communication very soon. Thank you very much. Dr. Dilip.
Thank you, Professor Ahmed Ali, for those nice words. And now it's the time for feedback. So I request one or two participants to share their feedback of this conference.
Professor, do you hear me?
Yes, sir. Yes. Yes.
Firstly, I am very happy to listen Professor Bhargava. I miss him, really. Hello, Professor Bhargava. How are you?
Thank you very much.
It is nice
Long time after met.
Yes. I am happy to participate at your conference every year. This is a very big honor for me. I am every time support all Indian conferences. As you know, this is my aim to make good connections and big scientific relations and scientific projects.
Very nice.
This is my aim. Really, due to coronavirus, we do not make to face. I hope in near future, the coronavirus virus is diminished completely. We give a chance to make face-to-face conferences is very fruitful. I believe that. I also happy to find Professor Supi Khan name. In the screen I find her name. I also would like to thank her. Yesterday I am not have enough time to follow the lectures because of my faculty position. I have some duty in the conference in the board, so I not catch some lectures. Sorry. It is very big work. I know the Kerala University have prepared this conference. I would like to thank all the teams of the conference, especially Professor Kumar. When I sent an email to him, he immediately followed, then responds to my email. When you need any help, any things, I am happy to help you. If you have need any special issue, we have this journal. I am happy to publish your special issue in our journal, Montessori's Pre-Interpolate Mathematics. This is a very nice journal. We are regular journal, international mathematical journal. This is a free of charge. There is no money, nothing. We are need to welcome your our journal. This is I read it. I do not know. In my word page, you find all, maybe this page is perfect. Montessori's current debate method. You read it? No?
Yes, yes.
Thank you very much. I say hello from Antalya to India. Thank you very much. Bye bye.
Thank you, Professor Yilmaz, for your nice words and for offering a possible publication of our proceedings. From the participants, I would like to hear some one or two feedbacks. Participants, anybody? Would you like to share?
Yeah, there is Rajendra Lekhawat, Dr. Rajendra.
Yeah, Dr. Rajendra, sir, you can please.
Yeah, this is Rajendra, sir. From
Yeah,
Mumbai.
you can switch on your video also.
All right, 1 second. This is Rajendra from Mumbai, sir. Basically, we are not given. First of all, I'm very. This is my pleasure to hear everybody here, basically, and I hardly missed any of the lectures whenever lectures are on this thing, special functions and all. I keep writing sometimes earlier also. I was keep writing for this particular thing, Professor Ali last time, if you remember. And I like most of the time, almost all the this one special functions lecture I have attended. These are very close to my heart, first of all, like in particular, and number theory in general. We are not given holidays, this one, Christmas vacation yet, but I took especially leave, like, you know, I applied for leaves and so that there should not be any disturbance and I should be able to attend right from, you know, right from each morning, each and every session till even I did not leave even paper presentation, just to see like how, you know, young enthusiastic people are, you know, working upon. So every speaker undoubtedly, like I have no words to say. They are obviously all excellent people, very intelligent and very knowledgeable ones. And it was very great pleasure of mine to listen to them. Thank you very much. And looking forward to all these kind of this thing. But point is like COVID, definitely, I'm very, what to say, it's like sad to see like some of the people have, you know, lost their kinsmen, their family members. But academically, to be very honest, I got a lot from, I mean, I was very happy that most of the sessions and most of the conferences I have attended during this COVID and all. And I'm very happy, like I met many people during COVID. Thank you a lot. Thanks a lot. I'll not extend much. Thank you very much. Thank you, everybody. Yeah. Thank you, sir.
Thank you, Rajendra, sir, for your nice words. And
yes,
anybody else wants to share their views or comments, or the negative comments are also welcome, in fact.
People can raise their hands so that we can call them.
Yes, yes.
मैंने चैट की थी वो वापस नहीं आ रहा है स्क्रीन पे कैसे
Yes.
As Dr. Dilip said, we are really happy to listen some criticism if you have. So that will be a good opportunity for us to improve upon.
Anybody wants to share some comments or their feedback, or anybody from outside the country? I hope many of them are, some of them are from outside also.
Okay, Dr. Dilip, you can go ahead. I think.
So thank you, participants, for their feedbacks. And now I request Professor Kalyan to say a few words.
Yeah, thanks a lot, Dr. Dilip Kumar, and respected Professor Bhargava, Dr. Ali, and all the distinguished mathematicians, the participants. As Professor Bhargava was pointing out, that there is an end to all the things that good that we get, and these 3 days, I'm sure that all the participants and have had a real great time, and it's all big credit. It's a mammoth work of the list that Dr. Ali pointed out, the number of papers presented, the number of speakers, and online mode, even if it is there are these technical glitches that come up here and there many a times. And it's really heartening to see the work that Dr. Dilip Kumar and his capable, his very efficient team of University Kerala, they put in. So a big hand to Dr. Dilip Kumar and all the organizers. It's a tremendous work to see at the end of the day that everything has gone off so well. And even though only few participants came up on the face to share few words, but I could read all the charts that is here. That's already a stamp of success of this conference, which goes to Dr. Dilip Kumar to large extent, and a big chunk of it to Dr. Ali also. I mean, I know how he just got up from various problems in from COVID to personal tragedies and all other things, but he took that one up, and I know how in a quick time Dr. Dilip Kumar agreed, and how this conference today we are successfully finishing off. So kudos to both Dr. Dilip Kumar and Dr. Ali for making it a huge success. And of course, Kerala, as I know, I'm here for more than 1 year, that how efficient, how efficiently the system works. Just to give a word, as Professor Bhargava was pointing out, we had Honorable Higher Education Minister, Dr. Bindu was there. And, it was really a pleasure to hear a minister, there was a little bit of EA was there, that many other places we have politicians who come up, and there will be very little academic that will be able to hear from them. But I assured them at that time that it will be a change for you, because I know I'm here, and so the government of Kerala, as Dr. Bhargava was pointing out, is all for the improvement of basic science even. I'm an institute here, which is a basic science institute, and I know how much support that I get directly from the head of the government. So it's a real, unfortunately, it is had to happen online. And had it been offline, you would have seen the hospitality, the efficient structure that they put in for all the programs that they do it here. So hopefully, as Dr. Bhargava, Dr. Ali, and all of us are pointing out, that this COVID era will cease. And next time we will have an offline with good interactions in the next ICSFA that will happen. And so I'm sure at the end of the day, conference, we may hear a lot of good things, but at the end of the day, the conference, I would call it a success if the young researchers, the young students who are sitting there and who can find motivation, can find new projects to work in. And we had very good speakers. I mean, we tried, Dr. Ali, Dr. Dilip Kumar tried their level best to get the top notches in the areas, in the special function, number theory, fractional calculus, and in every area that this conference covers. The top people really spoke. They were very generous, and we are all from the executive committee very thankful to all the speakers that they agreed readily. I mean, I know how Ken had difficulty. I mean, he had committed to many places. As you know, that Professor Ken Ono is a very, very popular speaker, not only just a researcher. So the request come from all over the world to him to really speak on this particular day. And he accommodated immediately. And so really thankful to Professor Ken for readily agreeing and supporting SSFA over the years. Professor Bruce Blunt is always there with us. And the rest of the speakers who spoke with us. So it's a great success, Dr. Dilip Kumar. And I'm happy to see, I can see the tiredness on your face and the amount of work that Dr. Ali also is giving us a little smile. But I know that behind, he was there all the time to see if there are any technical glitches, he will be there. So, thanks to all of you, and thanks to all the participants. And I'm very happy to see such a grand success of this particular conference. Thanks a lot.
Thank
And
you.
especially last words. Yeah, we are especially grateful to Professor Ali and Dr. Dilip for all their wonderful foot soldier-like work. Thank you very much. On behalf of everybody.
Thank you, sir. Thank you,
I hope you
Professor
heard me.
Kalyan.
Yeah, another thing I want to say about Dr. Dilip Kumar, you look like a movie actor. If it is a compliment.
And you also look like a movie star, Professor. You remember?
Me?
Yes, Paresh Rawal.
Oh. That's a negative role, perhaps. Negative role.
No, but he is a very good actor, but
Yeah, good actor.
yes.
Okay, thank you. Thanks a lot.
Okay.
Thank you, sir. Thank you, sir, for the for these words. Anyhow, I am just moving to the vote of thanks. Starting from the beginning, I would have to thank Professor R. Bindu, who was the Honorable Minister for Education, Higher Education in Kerala. Even though she was very busy, that she had cabinet meeting at 10:30, so she was insisting that I can give only maximum half an hour for you. If it is okay, then I can give her consent. But I was surprising that she delivered a very nice and motivating speech in the welcome and the inaugural session. And in fact, our Vice Chancellor, Professor P.P. Mahadevan Pillai, he was attending certain MAC visits. That is why he could not join our conference. Otherwise, he could have attended our conference. But in fact, our Pro Vice Chancellor, Dr. P.P. Ajay Kumar, has joined us and nicely felicitated or said his part. He has from the very beginning itself, he never says no to any activity. If we approach him, he always motivates us and encourages to do these type of activities. In fact, our university is always providing encouraging to do conferences with the most participants from India and as well as abroad. So it was nice. So I thank Professor R. Bindu, Professor P.P. Mahadevan Pillai, Professor Ajay Kumar for their part, for delivering their part in this conference. And next comes the role of SSFA. That SSFA, without the society, we could not organize such a big conference. It is the name of the society that the speakers are agreeing to deliver their talk. That is the main thing. So if I go personally to request them to deliver, they may say that I am not free. But if I say that it is for an SSFA conference, then even though they are busy, they will say that yes, I will be delivering a talk. So that is the advantage of SSFA, and that is the strength of SSFA in maintaining the research of the society for maintaining the research in special functions. So I would like to thank the current president of SSFA, Professor S. Bhargava, for the continuous motivation and this kind of enlightening words, who has definitely motivated the young minds like us for organizing such programs, and this has really inspired me to organize further conference in future also. So I thank Professor Bhargava, and also I thank the Vice President, Professor Kalyan Chakravarti, for his motivating words, as well as for the continuous encouragement, support, and for getting Ken Ono in this conference. He has played an important role in that. So for that, and I wholeheartedly thank Professor Kalyan for his efforts. And in fact, Professor Pathan, who has been traveling to USA, that is why he was not there. But his supports are like continuous support. We can, in any situation, we can call him like a father. I can call him and ask any kind of help, and he always helps me to organize such conferences earlier also. So on behalf of this Department of Mathematics, I sincerely thank Professor M.A. Pathan. And I would also like to thank Professor Ahmed Ali. Without his help, I could not have done this conference, because he has a very exact plan how this should go, the things should happen. This plan is already with him, and we just want to follow his ideas, that's all. So if I follow that exactly what he means, then the things will be going without any faith. So that is the way I could understand, and I could learn many things from him by organizing this conference. So I special thanks to Professor Ahmed Ali for helping me for doing this conference. And in fact, all the executive members of SSFA who were some way directly or indirectly participating in organizing the lectures, like Atul has given some names for our invited speaker list, Subhi Khan ma'am and other speakers are all benefit for this conference. So I thank all the executive committee members for their help and support. And moving further, I would like to thank Advocate Babujan, our syndicate members, Advocate K.H. Babujan, Dr. S. Naseeb, Dr. Gop Chandran, Dr. Gabriel Simon, who is the director of IQAC of our university, has all provided a very good support. In fact, Professor Naseeb has given me the contact number of this minister, so that I could contact him. So, but he could not attend the meeting because of some urgent matters. So in his absence, I extend my sincere thanks to our syndicate members, Advocate H. Babujan, Dr. S. Naseeb, Dr. Gop Chandran, and our IQAC director, Dr. Gabriel Simon. Next, I would like to thank all the invited speakers who were ready with their presentations at the time to time. When I sent a mail, they used to respond immediately when I request for the title, when I requested for the abstract, or whatever help is needed, they were ready to share it, and they reached the presentation on time. And in fact, I would like to say a special mention to Michelle, because due to some typing mistake, I put the wrong date. That is, in fact, I wrote it as 23rd. And even when I responded with an immediate mail, he responded, and immediately at the session he came, and on 22nd he delivered his talk. So that is the hospitality which he has shown, and that is I have invited him several times. So maybe that he has agreed to deliver his talk on December 22nd. So I especially thank all the invited speakers. I would, in fact, I would like to read the speakers, if you permit. Walter Vanashe, Professor S. Bhargava, who delivered the presidential address, Professor A. Matai, who is the past president and as a earlier president of this SSFA, then Professor Saminathan, who chaired the session, Walter Vanashe, who delivered the talk, Dimitri Kap from Israel, who delivered the talk, then Subhi Khan, who chaired the session and delivered the talk, Professor Kalyan, Professor Michelle Wall-Smith, then Ken Ono, Professor Ajay Shukla, Atul Dikshit, Subhi Khan, Virginia Kiryakova, Iva Kashlik, Francisco Mainardi, Sachin Palekar, Varsha Gedji, then Bruce Burns, K.R. Vasugi, Gaurav Bhatnagar, Yuri Lushko, Yilma Simshek, and R.K. Parma. So I thank all each one of the speakers who has come up with beautiful works in their area and motivating and informative works. So thank you very much for the sessions. And I would like to specially thank the chairs of the contributor paper session, the Dr. R.K. Jana, Ritu Goyal, S.K. Upadhyaya, A. Rias, Krishna Kumar, Deepa, H. Nair, all these people for spending their valuable time for chairing the session. It was 2 long sessions because 80 papers were presented, and giving each papers 10 minutes itself, it is a very big time. So thank you very much for them. I think they need a real congratulations for completing the sessions in time. So next, I would like to thank all the session chairs, all the participants. In fact, the participants are seriously attending the sessions, but I only had some regret that most of the people are hesitating to ask questions. But if questions are there, then only I think that the sessions will be live, and the students who are just started their work will get some idea or motivation. So at least I request the participants, at least from this forthcoming conferences, you please ask questions. In fact, I request all my students also to ask questions, but they are also feeling they are not having the courage to ask. That is what we have to that is what we have to break. So students should come with some courage to ask questions. And next, I would like to thank our head of the department, who is actually, he is like a friend to me. He always encourages and motivates to do all academic activities. Most of the academic, whenever there is an opportunity to organize an academic activity, our head of the department, Dr. Ramesh Kumar P, has always come forward. So I especially thank our head of the department for giving me an opportunity to organize this conference. And I would like to thank the other faculty members of our department, former head, the teachers, all for continuous support. And in fact, our statistics department is also supported us. One session was chaired by the faculty from statistics department. So I thank each one of them for their help and support in organizing this. Next, I would like to thank all the research scholars. In fact, I would like to tell their names, and if they are, please switch on their cameras. If you are in front of the this camera, you just switch on. Ajina, Susan, Arya, Akita, Fatima, Renjini, Judy, Adira Chandran, Akhil, Rehana, Megha Mohan, Anita, Ashik, Krishnan, Chintu, Atulya. All these students were there, all are these research scholars, and they were behind the parallel sessions which were conducted successfully. So I think I would like to thank each one of you for their efforts. In fact, today is a holiday, but they came here for my sake, and they were sitting here for a long time. I think they have taken their lunch only at 3 o'clock. So it is showing their seriousness and efforts that Akita, Renjini, all are here. So I thank you all for the continuous support you have provided for making this conference a success. So next, I would like to thank all the contributory speakers. Thus, without the papers, the conference is something like simply a show. It is the seriousness will come only when there are serious contributory paper sessions. We had, I think, 13 country participants were there, and from Algeria, from Morocco, from China, from Brazil, so many countries. We had from Malaysia, from Saudi Arabia, so many countries we had paper presentations, and all were there to present their papers. And thank you very much for selecting SSFA, the ICSFA, for presenting their papers. So thank you very much. And finally, I would like to thank all the postgraduate students who have supported, like Smriti, who compared our first session, Uma and Purnima, who delivered the prayer song, and all the others who were behind this conference. I would like to thank each one of them. And I would like to thank all the participants also who are they have not presented but have attended the sessions. So I I really thank each one of you for making this conference a grand success. In fact, I was thinking that the conference timing may change, but somehow I could manage. The sessions were on time and more or less ended in time. So I really thank all the participants, organizers, and respondents of this conference. And finally, a few words about the certificates. We will be issuing you the certificates within 2 weeks. A feedback form is shared in this link. So please fill the feedback form and you will get a certificate within a week. And regarding the proceedings, I think Professor Ahmed Ali has already communicated. So we will be getting back to you with the proceedings of this conference. So thank you very much for the continuous support all of you have provided, especially SSFA. And thank you very much for considering the University of Kerala for hosting this event. So I really thank for that. I thank because you thought that I have the courage to organize this. I was not sure that I could have organized this. But
Professor and Professor Kalyan, there is one last remark I would like to put. In fact, I have heard so many times Professor R.P. Agarwal saying we should train next generation who can take the lead. And before last year, we inducted 2 new bloods, young bloods. And last year, Atul did a lot in organizing this conference successfully, and is a very well-known mathematician, very dynamic. And this year, another person that we had inducted, Dilip, has shown his worth. So we can assure ourselves that this will go on. The show will go on. And we look forward for the more people, young people, to come and join us who can take the lead. Thank you. Thank you, Dilip.
So thank you, sir. Thank you all for this attending the sessions. So thank you. And with your permission, I declare that the conference is closed.
Yeah. A big hand to Dilip at the end. Yes, thank everybody. So thank you, Dilip.
Thank you very much. Thank you, everyone.
Yeah. Take care. Take care.
Thank you, sir. Thank you.
Thank you. Thank you, sir.
Yeah.